Greetings and welcome to InnoX 2021. This is Group 7 from EXTC-DBIT, and the topic of our project is the design and development of mobile handset antenna for optimum SAR in mobile communication systems. And we have been working under the guidance of Ms. Frida Carvalho. In this video presentation, we shall be guiding you through the progress of our project, and we shall also be exhibiting the results that we obtained during this progress.
Whenever we call someone by a cell phone, there is transmission and reception of RF signals. During this transmission and reception, most of the signals fall upon the device, that is a cell phone. But some of it also gets absorbed into whatever there is in its close proximity. This can be a head or any other object. This absorption of RF signals can have certain harmful effect on a human body. It may penetrate through the tissue and instigate tumor. Other symptoms include sleep disorders, headaches, restlessness, irritability, etc. According to a report by International Telecommunication Unit (ITU), there were 5 billion phone subscribers in the year 2011. This was the case 10 years earlier. Now, the scene has totally changed. The total number of mobile subscriptions have exceeded the 8 billion mark, and is 8.3 billion subscriptions in the year of 2019. The growing concern about the detrimental effect of human health is what motivates us towards designing a low SAR antenna.
In today's world, electronic gadgets have become a part and parcel of our lives, from air conditioners all the way to the vehicular transports that we use. However, among these devices, the most prominent and the most sought after devices are mobile phones. Over the last few decades, our mobile phones have come a long way from a luxury item all the way to a necessity, especially in these days when our only window to the world is our mobile phone. As a matter of fact, most of us millennials start our day by checking our phones for updates. Unfortunately, this very gateway is a source of various radiations that can be fatal. The RF radiations emitted by a mobile phone is never constant, however. It varies constantly depending upon the angle at which the mobile phone is held, all the way to the place in which it's being used. Hence, for ensuring the safety, the highest value is always considered. This is where SAR comes in the picture. Now, SAR stands for specific absorption rate. SAR values increase as the conductivity of human body tissue increases, and usually decrease as the increase of the relative permittivity of the human body tissue increases. Hence, it is mandatory for all mobile handset manufacturers to calculate SAR values produced by their products in order to ensure the safety of their consumers. It is calculated using the formula sigma by rho the whole into E square, where sigma stands for tissue conductivity, rho stands for tissue density, and E is the electric field. Excessive SAR levels may lead to elevated temperatures, thus meaning that RF radiations emitted by the mobile phones have various short and long-term effects on the human body. The short-term effects include headaches, dizziness, lack of concentration, poor vision, stress and anxiety, whereas the long-term effects include brain cancer, thyroid gland cancer, and increased risk of miscarriage.
Okay, so now after understanding all the things about SAR, let us now have a look at SAR value. To find the SAR value of our cell phone, just open your dial pad and type *#07# and call it. You will find your cell phone's SAR value.
Let's take a look at our problem statement. For our problem statement, we are to design and simulate PFA planar inverted F mobile antenna operating at 900 MHz GSM band for a mobile communication system. The SAR limit for this antenna structure would be below the maximum permissible limit directed by the FCC body. The maximum SAR limit for India is 1.6 watts per kg averaged over 1 gram of human tissue.
Let us now see the work which we have followed. The first thing which comes under the work is the methodology. First step towards our project was to do the literature survey on what is SAR, because this was the foundational and the most basic step. Then, after understanding what SAR actually is, we studied about different mobile phone antennas, as because there exist different antennas like microstrip patch antenna, PFA antenna, etc. We then shortlisted PFA antenna for GSM application. After shortlisting, we designed and tested the antenna. We then did some research on methods to reduce SAR. Then we implemented the first method of water walls and tested it. Then we adopted the second method of conducting walls and then tested it. After implementing the first two methods, we then implemented the third method of EBG. After all the implementation, we compared the simulation results.
Let's talk about GSM. GSM stands for Global System for Mobile Communication. It is a digital cellular 2G technology used for transmitting mobile voice and data services. The popular GSM bands are GSM 850, GSM 900, GSM 1800 and GSM 1900. The primary cellular antenna will mostly have both a low band somewhere between 700 and 960 MHz and a high band somewhere between 1710 and 2700 MHz. There are a couple of things to note about frequency bands. The number of frequency bands expands every year. Also, many of the bands overlap. For instance, GSM 850, UMTS band 5 and LTA band 5 are all the same frequency range. Hence, an antenna that works well for one of these bands will largely work well for the other bands. Some advantages of using GSM are improved spectrum efficiency, compatibility with ISDN and other telephone services, and international roaming. Second, mobile phone antennas. There are multiple antennas on each phone which perform different functions. To talk about some, primary cellular antenna, GPS antenna, Wi-Fi antennas, NFC antenna, etc. Among them, the most important is the primary cellular antenna because it is used for transmission and reception of mobile calls. Hence, many specifications and requirements are to be met before finalizing the antenna for a particular application. Upon research, we found out that for a primary cellular antenna, mostly a monopole antenna or a PFA antenna structure is used. So let us get to know about them. A monopole antenna consists of a straight rod-shaped conductor mounted perpendicularly over some type of conducting surface called a ground plane. One side of the antenna feed line is attached to the lower end of the monopole and the other side is attached to the ground plane. The monopole is often used as a resonant antenna. The rod functions as an open resonator for radio waves. Therefore, the length of the antenna is determined by the wavelength of the radio waves used. The most common form is the quarter wave monopole, in which the antenna is approximately 1/4 of the wavelength of the radio waves. The main advantage of using a monopole antenna are omnidirectional pattern in the horizontal plane, easy design procedure and lightweight. The drawback of the monopole antenna is that it has a low radiation efficiency. Now talking about the PFA. PFA, planar inverted F antenna, consists of a rectangular planar element located above a ground plane, a shorting circuit plane or a pin, and a feeding mechanism for the planar element. PFA is a variant of the monopole where the top section has been folded down so as to be parallel with the ground plane. This is done to reduce the height of the antenna. Advantages of using PFA as a primary cellular antenna is: number 1, having reduced backward radiation towards the user's head, that is by minimizing the electromagnetic wave power absorption and enhancing the antenna performance. Second, PFA exhibits moderate to high gain in both vertical and horizontal states of polarization. This feature is very useful in certain wireless communications where the antenna orientation is not fixed and the reflections are present from different corners of the environment. PFA has a drawback, that is narrow bandwidth.
We all know by now that SAR is used to determine the amount of radiation that a human tissue absorbs. This measurement is especially important for mobile telephones which radiate close to the brain. Now, in order to obtain the most efficient results from our simulations based on this study, we created a head model representing 6 layers of human tissues present in the human head. In other words, we created 6 concentric spheres which represent 6 different tissues. These human tissues have different electrical properties like permittivity and conductivity depending upon the frequency, as well as geometry, tissue size and also water content. The 6 different tissues are namely the skin representing the outermost layer of the human head, the fats that are present under the tissue, the bone representing the skull, the dura, which is the thick membrane made of dense, irregular connective tissue that surrounds the brain, and the CSF, cerebrospinal fluid, which is a clear fluid that surrounds the brain and the spinal cord, and finally the brain.
Presenting to you the design architecture. Now imagine yourself lying down on your side with the mobile phone over your ear. This is exactly what you see in the picture here. The peach color circle is representing the human head with all 6 layers of the human head model. The antenna and the head are separated by a thin plastic layer which represents your mobile phone case. We have used a single band PIFA antenna. PIFA consists of 5 basic elements. They are: number 1, a large metallic ground plane, black color in the image. Second, a resonating metallic plane, green color in the image. Third, a substrate separating the two planes, that is the dielectric. It is blue color in the image. Fourth, a shorting pin, a thin purple color strip which runs from the patch to the ground plane. And the fifth, a feeding mechanism, a copper SMF connector in the image. The exact dimensions used are displayed. Upon simulation, we find out the SAR of this antenna to be 1.844 watts per kg. The return loss is found out to be minus 6.65 dB at 0.87 GHz.
Let us now have a look at all of the 3 SAR reduction techniques in detail. The 3 methods are the water wall, the conducting wall, and the electronic band gap, the EBG structure. Starting with the water walls method. In the original basic antenna, we just added 4 walls made of water below the ground plane, which is black in color over here, of dimension 0.166 mm in thickness, 100 mm and 50 mm in length, and 5 mm in height. Here we can see the side view and the front view. Talking about the specific absorption rate, the maximum specific absorption rate which we obtained is 1.2624 watt per kg. This value is less compared to the original antenna's specific absorption rate value of 1.84 watt per kg. The return loss and the radiation pattern is almost the same as that of the original antenna, so the antenna parameters didn't change after adding the water walls.
For our second SAR reduction method, we have used a low SAR antenna that we had designed earlier and attached 2 vertical side walls made of copper in order to reduce the radiation towards the human head. Simulations and measurements agree and show that the SAR of the proposed structure has reduced by 81.135%, 0.34787 watts per kilogram at 0.9 GHz. Also, the return loss is reduced to minus 27 dB, which is optimum.
The third SAR reduction technique is EBG. EBG stands for electronic band gap. They are artificial periodic objects that prevent or assist the propagation of electromagnetic waves in a specified band of frequency for all incident angles and all polarization states. EBG is used because it eliminates the drawbacks of conducting surfaces, prevents the propagation of surface waves, lowers the antenna profile, and improves radiation efficiency, also increases antenna gain and reduces back loops. In the bottom image, if you see, there are periodic square patches created on the bottom of the dielectric. They are 5.5 mm in dimension. Upon simulation, the SAR value comes out to be 0.1152 watts per kg and the return loss is minus 6.67 dB for 0.87 GHz.
After looking at all of the 3 methods, let us now have a look at the final results of our project. Basically, the summary. The final results is the comparison of all of the 3 methods which we have implemented. The SAR value of the original antenna came out to be 1.8440 watt per kg. This value is above the FCC limits of 1.6 watt per kg. After implementing the method 1 of water wall, we got a SAR value of 1.2624 watt per kg. This value is below the FCC limits. The SAR got reduced by 31.54%. Then we implemented the method 2 of conducting walls. We got a SAR value of 0.34787 watt per kg. This value is also below the FCC limits. The SAR got reduced by 81.135%. Then we implemented the method 3 of EBG, the electronic band gap. We got a SAR value of 0.1125 watt per kg. That is also below the FCC limits. the SAR got reduced by 93.8%. So the basic inference which we can draw from this table is that the EBG structure, electronic band gap structure, is the most optimum structure for a particular antenna.
In conclusion, the progress of the project can be summarized as follows. Firstly, physical implementations are always one of the most important considerations when it comes to designing antennas. The designs mentioned above, the EBG structure, due to its compact size and positioning, has a comparatively idle design when interfacing with a FIFA antenna. On the other hand, the use of conducting walls and water walls, though effective, upon implementation would tend to make the design bulkier. In all the proposed designs, upon comparing the obtained results to the results of the basic antenna, the return loss has always been taken into consideration. This is because in an antenna, the return loss is a figure that indicates the proportion of radio waves arriving at the antenna's input that are rejected as a ratio against those that are accepted. On comparison between the three techniques, adding conducting walls to the antenna produced the best return loss by improving it to minus 27 dB. Finally, coming back to the essence of our project, through analyzing the interaction mechanism of the radiation fields of mobile phone antennas with nearby human tissues using boundary conditions of electromagnetic fields, we find that the SAR values produced by the EBG structure is the lowest and hence the most efficient.